I want you to imagine something for a second. You're cooking, maybe you lean over the counter and your hand touches a hot stove.
Hmm.
What do?
You pull it back instantly.
Instantly. You don't form a committee in your brain to weigh the pros and cons of getting burned.
No, it's a reflex.
Exactly, a reflex. But now, let's imagine something else. You have to organize a cross-country move. You've got, I don't know, 40 boxes, a rental truck, a new lease in Chicago, and a cat that has a total meltdown in the car.
Right. You can't just reflex your way through that one.
No way. If you did, you'd end up with your cat in Delaware and your furniture in a ditch somewhere.
Which brings us to what we're talking about today. We're moving beyond those simple reflexes into the real heavy lifting of intelligence. We're talking about planning.
Specifically, classical planning in AI.
It's such a critical distinction. We often think of AI as just thinking, but a huge part of the field is really the study of rational action.
It's not just about knowing things.
Exactly. It's about creating a sequence of steps to change the world from how it is to how you want it to be.
So we've talked about search algorithms before. Why wasn't that enough? Why did we need this whole new field of classical planning?
It really comes down to two things: scale and structure. The early methods, they treated the world like a black box.
A black box.
Yeah, an atomic representation. The AI sees state A and state B and knows it can get from one to the other, but it has no idea what's inside those states.
So it's like it knows the names of streets in a city, but it doesn't know that streets are made of pavement or that cars drive on them.
That's a great way to put it. And because it can't see the structure, you, the programmer, have to hand code every single possible move. It just doesn't scale. If you try to use simple logic, like in the Wumpus world we've talked about, it gets completely swamped.
Swamped how?
Combinatorial explosion, just a ridiculous number of possibilities. Even a simple world with 10 objects that can move around has an astronomical number of potential states.
And that leads us to this classic problem in AI. A problem so infamous, it has its own name. The frame problem.
Ah, yes. The nemesis of early AI. It's the problem of describing what doesn't change.
Which sounds easy. You just say, nothing else changed.
But in formal logic, you can't be that vague. You have to be explicit. If I pick up this pen, the pen's location changes, but the color of your shirt didn't change. The Eiffel Tower is still in Paris.
You'd have to list every single thing in the universe that stayed the same.
You basically had to, yes, you'd spend more computing power confirming the moon is still in orbit than actually solving your problem. It was a total dead end.
So the AI community needed a hero, and they got one.
Yeah.
In the form of something that sounds like a government agency. PDDL.
It does have a bureaucratic ring to it, doesn't it? Planning domain definition language.
Catchy.
But it was a complete revolution. It let AI move from those atomic black boxes to what we call factored representation.
Okay, factored representation. Break that down for me.
So instead of one big indivisible state, we break the world down into variables, or facts. We call them fluents.
Fluents.
Yeah, think of them as the basic truths about the world that can change. So in an air cargo problem, a fluent might be at plane 1 Melbourne. It's a single specific fact.
Okay, so we have a list of these facts. At plane 1 Melbourne, in cargo 1, plane 1, that sort of thing.
And right there, PDDL pulls its first clever trick, the closed world assumption.
Meaning?
If a fact isn't on the list, the AI assumes it's false.
Oh, I see. So you don't have to list all the places the plane isn't.
Exactly. You don't have to say not in Sydney, not in Tokyo, not on Mars. That alone saves an incredible amount of memory.
Okay, so that's the state of the world.
Right.
But we need to do things. We need actions.
Right, and for that, PDDL uses action schemas. Think of them like recipe cards for the universe. Instead of defining one specific action like move plane 1 from New York to London, you define a general template.
Like fly plane from Paris.
Precisely. And that template works for any plane, any start, any destination, as long as it meets the preconditions.
The fine print.
Exactly. The precondition is what must be true before you can act. To use fly, SFO, JFK, the precondition is that the plane P must be at SFO. You can't leave a place you aren't at.
Makes sense. So if the preconditions are met, you fly. What happens then?
Then you get the effect, and this is where PDDL so elegantly solves the frame problem. The effect is broken into two simple lists, an add list and a delete list.
So walk me through that.
When the plane lands at JFK, we add the fluent HEP JFK to our list of world facts.
Okay.
But critically, we also delete the old fact HEPSFO.
And that's it. You don't mention anything else.
Nothing else. The Eiffel Tower, your shirt, everything else is just assumed to carry over. We've turned that massive logical nightmare into a simple list update.
Okay, so PDDL gives us the language. We can describe the world and how actions change it. But that's not the same as solving the problem. We still have to find the path.
Right. Now comes the search. And there are two main ways to go about it, forward or backward.
Well, starting at the beginning seems logical. Forward search, you look at where you are, see what you can do, and pick a path. We call it progression.
It's definitely intuitive. But in planning, it's very often a trap.
A trap? Why?
The branching factor, the number of choices. Let's use the book buying example from the source. Your goal is to buy one specific book, say Frankenstein. The action schema is buy ISBN.
And there are, what, millions of ISBNs?
Billions.
Yeah.
So if the AI is just blindly searching forward from its start state, it sees the buy X action and it generates a possible next step for every single book in existence.
So it starts exploring the path of buying a cookbook or a tractor manual.
All of them. Just mountains of totally irrelevant actions. The search space just explodes. A simple air cargo problem with 10 airports can have 1055 states.
That's more than the number of atoms in the known universe.
By a lot. You cannot brute force your way through that.
So we flip it. We start at the end and work backward. Regression.
Exactly. You start at the goal. The goal is at plane 1 JFK. You ask what action could possibly result in this state.
Well, an action that involves flying to JFK.
Right. It's a relevant states search. You immediately ignore buying books or painting a fence or flying to Tokyo because none of those actions achieve your goal. You only look at what matters.
But there was a concept here that really tripped me up. When you go backward, the delete list is treated differently.
This is a crucial and kind of tricky point. When you go forward in time, you delete facts that are no longer true. But when you are rewinding time from the goal, you ignore the delete list.
Why? I don't get it. Wouldn't that corrupt the state?
Okay, think of it like this. Your goal is to be in a room. The action that got you there was enter door. When you rewind that action, you know you no longer need to be in a room.
Right.
But let's say the enter door action also had a delete effect, not in hallway. When we're going backward, we don't know for sure that you were in the hallway before. You could have been in the kitchen or outside.
So adding in hallway back into the requirements would be making an assumption.
A huge assumption. It's about not overcommitting. We only care about what is absolutely necessary to make the previous step possible. It keeps the state we're searching for as general as possible.
Okay, so backward search is more focused. But even with that focus, big problems are still, well, big. We need a shortcut. And this is where AI gets a little sneaky.
I'd call it clever. This is the world of heuristics.
I call it cheating. The AI basically solves a hard problem by first pretending it's solving a much easier imaginary version of it.
That's a perfect way to describe it. We call it relaxation. We literally relax the rules of reality to get a quick estimate of how hard the problem is.
Like the first method, ignore preconditions.
Right.
The AI just assumes it can do anything, anytime.
Exactly. What if you could just teleport cargo instantly? The problem just becomes, how many teleports do I need? It's not a real plan, but the answer, say 5, gives the AI a hint. It's heuristic that says you are roughly 5 steps away from the goal.
But the other method is the one that sounds truly bonkers. Ignore delete lists. The source calls this the have cake and eat cake heuristic.
It's a classic. In the real world, if you perform the action eat cake, you add the fact eaten cake, but you delete the fact have cake.
A sad universal truth.
But in this relaxed version, the AI pretends the delete list doesn't exist. It assumes that after you eat the cake, you get the benefit of eaten cake, but you also still have cake.
Wait, hold on. How is that helpful? If the AI is building a plan based on the idea that it never runs out of resources, isn't the plan it finds just complete nonsense?
The plan itself might be, but the length of that nonsense plan is incredibly useful heuristic.
Yeah.
Because it allows for what we call monotonic progress. You're always getting closer to the goal, never taking a step back by using up a resource. This makes it really easy to calculate the absolute minimum number of steps required, even in a perfect magical world.
So it's like an optimist's first draft.
It is. The AI says, okay, best case scenario, if nothing ever went wrong and I had infinite fuel, this would take at least 8 actions. And that number, that 8, is a fantastic guide for the real search algorithm, which then has to deal with reality.
It's almost philosophical. To find a realistic plan, you have to start by imagining a fantasy.
And it works stunningly well. So now we've got the language, PDDL, and we've got these clever heuristics. But there's one specific tool that really brought it all together: the planning graph.
Right, the graph plane algorithm. This isn't just a search tree, it's something different.
It's a different data structure entirely.
Yeah.
A normal search tree grows exponentially. It gets too big too fast. A planning graph is polynomial. It stays a manageable size.
And it maps out time in these layers. State 0, then action 0, then state 1.
Then actions 1, and so on. But the real genius of the planning graph is a concept called mutex, mutual exclusion.
This is the key part.
Yeah.
It doesn't just show what can happen, it actively tracks what cannot happen at the same time.
Yes, it draws these little gray lines between things that are in conflict.
Give me an example of a mutex.
Okay, an easy one is inconsistent effects. You have an action, paint wall red, and another paint wall blue. You can't do both at the same time to the same wall. The outcomes is wall red and is wall blue are mutex.
Or eating the cake and having the cake.
That's another perfect one. The graph builds up layer by layer, propagating these mutex relationships forward. It figures out all the potential conflicts in advance.
And at some point, the graph levels off.
It does. It reaches a point where no new facts or conflicts are being discovered.
Huh?
And at that point, you can just look at the final layer and ask, are all my goal facts here, and are any of them mutex with each other?
If they are, you know the goal is impossible.
It's impossible. You can stop right there. You've proven there's no solution without ever doing the full, expensive search.
And if the goal is there, and the facts aren't mutex,
Then you start the second phase. You do a backward search through the graph to extract a valid plan, making sure you never pick two actions that have a gray mutex line between them.
it feels so much more structured. Now, PDDL and graph plans seem like the big players, but there must be other ways to skin this cat.
Oh, absolutely. Some people looked at that 10 number and said, forget searching, let's just turn this into a giant math problem. That's S8 plan.
And CT like the college admissions test.
SAT as in Boolean satisfiability. They translate the entire planning problem, every possible fact at every possible time, step into a single, massive, logical formula of true and false variables.
That sounds completely unreadable for a person.
Oh, it's hideous. But for a modern computer, for a SAT solver, it can be incredibly fast. You just hand this giant equation to the solver and it spits out a solution if one exists.
And on the total opposite end, you have the more philosophical approach, situation calculus.
Right, that's a very rigorous first-order logic approach. It thinks about history as a series of situations. A situation is a snapshot of the world after an action. It's very elegant, but often harder to make efficient.
The other one I loved was the one that solved the shoe and sock problem, partial order planning.
Yes. Most planners want to create a straight line. Do A, then B, then C. But think about getting dressed.
You have to put your left sock on before your left shoe,
Yeah,
and your right sock before your right shoe. The order of left foot versus right foot doesn't matter.
exactly. They're independent. A linear planner wastes time trying to decide whether to do the left foot first or the right foot first.
So partial order planning just doesn't decide.
It follows the principle of least commitment. It doesn't lock in an order until it's absolutely forced to. The plan isn't a straight line. It's a web of actions with just a few ordering constraints. It's much more flexible and efficient.
And this isn't all just theory in a lab. This stuff actually went to space.
It did. The remote agent on NASA's Deep Space One mission. It used these exact principles of planning to autonomously control the spacecraft, diagnose problems, and achieve its goals millions of miles from Earth.
Which has to be the ultimate test case. You can't exactly send a technician if your plan fails out there.
No, you can't. It was a massive validation that this way of thinking, of reasoning about actions and effects, really works.
So if we zoom out, we've gone from a simple reflex like pulling your hand from a stove to these incredibly sophisticated systems that can model the world, find conflicts in the future, and navigate these insane possibility spaces.
And it's all about one thing: controlling that combinatorial explosion. The world is just too big to check everything. Intelligence in this context is about knowing what you can safely ignore.
You know, I'm still stuck on that ignore delete lists heuristic. The idea that a powerful strategy for solving a hard problem is to first pretend your actions have no negative consequences.
Well, it's a really profound insight, isn't it?
It makes me wonder, is optimism a fundamental computational strategy? I mean, if we as people truly calculated every single potential downside of every action before we did anything, would we ever even get out of bed in the morning?
Maybe not. Maybe you need that initial optimistic, relaxed plan just to get started, and then you bring in reality to figure out the details.
Something for all of you to think about. The next time you're planning anything, from a dinner party to a career change, ask yourself, Are you searching forward from where you are or working backward from where you want to be?
And are you maybe ignoring a few delete lists to make it seem possible?
Just probably don't ignore the delete list when you're packing the cat.
Definitely not.
That's all for this deep dive into the art of rational action. Thanks for listening.